In this section of chapter 3, we'll discuss about alkenes and two types of isomers we call cis and trans isomers. Just to remind you, alkenes are compounds with carbon-carbon double bond. So let's write down one alkene as an example just to refresh your memory. So this is an alkene without the hydrogens, obviously, and this is the functional group for alkene. Here we're going to talk about naming of alkenes. Just like naming of alkane, you select the longest carbon chain. However, in this particular case, the longest chain must contain the functional group. In this case, functional group is carbon-carbon double bond. Because this is alkene, it must have a double bond. So the longest chain that you must have should contain the carbon-carbon double bond. So on the left hand side, this is the right longest chain, but on the right hand side, this is not right, because here the longest chain is shown here doesn't contain carbon-carbon double bond. There is a carbon double bond, but not carbon-carbon double bond, because this is left out. So this is the longest chain, and name would be based on this longest chain. Now let's count the number of carbon. 1, 2, 3, 4, 5. So I have 5 carbon in the longest chain that also contains the double bond. So obviously it's going to be pentene. Now we need to number the location of the double bond, as well as substitution group that we have here attached to the longest chain. In this example, we have a 6-membered carbon-carbon longest chain. So obviously 6-membered carbon-carbon must have, for saturated carbon, must have the ending hexane, but since you have a double bond here, it's going to be hexene. On the left hand side, this is old type of naming. In most books in recent days, we write down functional group at the end with the location of the functional group. Now the question is, how do I determine the location of the functional group? In IUPAC naming or systematic naming, you consider the numbering in such a way so that in this case the double bond gets the smallest possible number. So if I assign the rightmost carbon to be 1, in that case 1, 2, 3, 3 will be the location of the double bond. Now 5th is the location of the substitution group on the carbon. The rule says that if double bond is equidistant from both ends, in this case that's the case. If I start numbering from far left, third location, you have the double bond. So it's equidistant no matter whether your numbering starts from far left or far right. So in that case, you make sure you pay attention to substitution group. So if C double bonds is equidistant from two ends, begin with the end near the first branch point. Basically, branch point must get the smallest possible number between the two. So in one set of numbering, this branch point gets 2. Another set of numbering, it gets 5. So obviously the top one is the right set of numbering. And that's why we name this molecule like this. E and E at the end because of its alkene. The location of alkene or functional group is 3, so it's a 3-ene. And then this is hexene because of 6 carbon. Hexa means 6. So hex 3-ene. And then the second location, you have methyl group. So that's why we say 2-methyl hex 3-ene. This is an old type of naming, and a lot of old books have this naming. Both are right, but this is something that we'd be using most often. Now, if you have a number of substitution groups, you arrange them in alphabetic order, just like naming of other alkanes. So we already talked about that we need to indicate the position of C double bond C, and if there is more than one C double bond C, we can use diene. Diene means there are 2 double bonds. Triene means 3 double bonds. So keep that in mind. In this particular example, again, you got the longest chain with 2 double bonded carbon. So this is one double bonded, this is the other double bonded carbon. So if I number from this end, 1, 2, 3, 4, because that not only gives the first double bond the lowest number, it also gives the substitution group the lowest possible number. So it is diene because there are 2 double bonds, and the location is 1 and 3. So 1, 3 diene. And then it is butadiene because there are 4 carbons. So it's the butadiene, buta 1,3 diene, and 2 methyl. The methyl is in position 2. Now this is cycloalkene. Again, first count the number of carbon atoms. Here each corner has a carbon, like this has a carbon. So 1, 2, 3, 4, 5. So this is a 5 carbon cyclic compound. 5 carbon compound will be pentane. This is a compound with double bonds, so it will be pentene. And obviously it's a cyclic compound, so you must say cyclopentene. Now here the rule is cycloalkenes gets C1 and C2. So in other words, if I have a double bond, one of them would get 1, the other one would get 2. And if you have a substitution group, that must get the lowest possible number. And that's why my numbering starts from here. So this is 1, 2, then 3, 4, 5. So how do I name this compound? 1, 5, because these are the same methyl group. This is a methyl group, this is a methyl group. 1, 5 dimethyl cyclopentene. Let's try to name this compound. In this case, you can see a ring structure with 7 carbon because each of these corner has a carbon. Okay, so that's why it's heptene, because you have a double bond there. So heptene, we end up with this. It's a cyclic structure, so it's a cycloheptene. Since double bonded carbon must get 1 and 2 in a cyclic structure, so I have 1 and 2 assigned. But the question is, can you also have 1 and 2 like this? Are they identical? Answer is no, because if you start numbering like this, it'd be 3 in here, 4, 5, then this carbon gets 6, where you have 2 substitution groups, and those substitution groups are nothing but methyl. On the other hand, if you follow the black numbering, this is the black numbers 1, 2, 3, then 4th position has 2 methyl group. Obviously, we'd go by these black numbers because that gives the smallest value to substitution groups, in addition to giving 1 and 2 to double bonded carbon. So now we can write down this name, 4-methyl, 4-methyl. Rather than writing down like that, we write down 4, 4 dimethyl. Di means 2. Methyl cycloheptene. So that's the name of this compound. Next, we're going to do problem 331, 3.31a. We're going to draw a structure for 3-propyl hept2ene. So let's first write down the end part, hept2ene. So I'm going to write down that hepta means 7. 1, 2, 3, 4, 5, 6, 7. Now let's assign number. It doesn't matter from which end you start numbering. 3, 4, 5, 6, 7. Since it's hep2ene, in the second position you have a double bond. Then it says that 3-propyl. Propyl means 3 carbon group. Now there are 2 types of propyl. One is isopropyl, where there's a branching next to the last. And this is just a simple propyl. And that's at location 3. So third location, I must have propyl. It's a 3-carbon group. So let's highlight that. So now let's double check whether my name is all right or not. In the third position, I have propyl, so it's a 3-propyl. Then it's hep2-ene. In the second position, we have double bond. In this case, we are showing you cis-trans isomers. Since you have a double bond, there is a restricted rotation. That means you can't move these methyl groups. So they're pretty much locked in this position unless and until you break a bond. So in other words, when you have something like this, two substituent groups attached to the double bond, if they're on the same side, is cis. So in this case, you get cis. In the second structure, these substituent groups are on opposite side, so that's trans. So how would I name this compound? The first one would be cis-but-2-ene. Why but? The longest chain still has 4 carbon. 4 carbon would be butane. When it has a double bond, it becomes butene. So that's how we get but-2-ene, because the location of the double bond is second position, no matter whether you start numbering from far left or far right carbon. In naming, you ought to get the longest possible carbon chain with carbon-carbon double bond. And since this is cis structure, that's why we write down cis at the beginning. Keep something in mind. After cis, there is a dash. Then after but, there is a dash. Then 2. Then again another dash, ene, which is the name of the functional group. In second structure, again, the longest chain. In naming the compound, longest chain is this. That is 4 carbon. So that's again butene. And the location of the double bond is 2. Because it doesn't matter how I start numbering. Let's number it from this end. 1, 2, 3, 4. So that's why it's but-2-ene. Now this is a trans isomer, so you write down trans. So first, in naming a compound, first you examine whether it has a double bond or a ring structure. When you have a double bond or ring structure, then there is the possibility of having cis-trans isomers. When two substituent groups attached to the carbon-carbon double bond is on the same side, then it would be cis. If they're on the opposite side, it would be trans. Now, I've been using the word substituent group in 2 different contexts. In this case, in longest chain, there could be substituent group. With carbon-carbon double bond, there could be substituent group. In double bonded carbon, substituent group is the group other than hydrogen that are bonded. Now, this is a problem from the book. Question is whether there is a cis or trans isomer possible. On the left-hand side, you can see that this is the methyl group. Remember I mentioned to you about the substituent group. You must have 2 substituent groups to have cis or trans, but there is no other substituent group, so obviously there will be no cis or trans. In part B, the groups that are bonded to carbon-carbon double bond is methyl, methyl, methyl. There are 3 methyl groups. If I had 2 methyl groups, then I could have said whether it's on the same side or opposite side if those methyl groups are bonded to 2 different carbons of the double bond. In this case, since there are 3 methyl groups, we cannot say cis or trans, because if I focus on this methyl group and this and forget this one, then it will be trans. On the other hand, if I forget this, ignore this, and focus on this methyl and this methyl, then it's going to be cis. So as you can see, that since there are 3 different substituent groups attached to carbon-carbon double bond, you cannot assign cis or trans. So there'll be no cis-trans. On the other hand, in part C, you can see that 2 Cl on the same side of carbon-carbon double bonded compound, so cis. In the next case, they're on opposite end, opposite side, so that's trans. So whenever you have more than two substitution groups attached to two carbon, then you'll have to use a different type of designation for isomers. So we're going to discuss in the next section a new type of designation of isomers, which we will be calling E or Z rather than cis or trans. Now 3.6a has already been discussed in previous slides, so here we're going to discuss 3.6f on page 85. In this case, formula is not given, rather name is given. So can we draw a structure based on the name? So let me write down first the name as given in the book, 3-methyl So 3-methyl hept 3 in. So the question is, can cis-trans isomer exist for this compound? First, I need to draw the structure. Hept in. So obviously, it's a 7-membered carbon. So let me write down the 7-membered carbon for hepta. 1, 2, 3, 4, 5, 6, 7. Since it's heptene, it would be helpful if I start numbering from one end. It doesn't matter which end. 1, 2, 3, 4, 5, 6, 7. So in the third location is a double bond. So let's have a double bond. So that's hept 3 in. Not only that, on the third location is a methyl group. So that's the methyl group, obviously without hydrogen. We left out hydrogen so that we can better see the connectivity. So this is 3-methyl hept 3 in. Now the question is, can it give cis-trans isomers? In order to get this answer, you have to focus on this carbon-carbon double bond, because cis-trans would be around this double bond. In a ring compound, it would be around a ring compound. Now, it would be helpful if I write down hydrogen. This carbon, number 4, has 1 hydrogen. Carbon number 3 doesn't have any hydrogen because it already has 4 bonds. So now, if I want to write down structure of this compound a little differently, because you know that this carbon 3 and 4 have sp2 hybridization, so angle will be 120 degrees. So I'm going to now write down differently. So this C double bond C and the 2 bonds. So around carbon 3, I would have this group. That's an ethyl group. So let's write down like this. That's the ethyl group, because the 2 carbon. And here you have the methyl group. The other one has the methyl group. So let's circle that. On the other end, that's carbon 4, has hydrogen and has propyl group. So let's write down 1, 2, 3. I'm writing down a little zigzag manner because these angles are 109.5. Now the question is it going to be cis or trans? As you can see here, there are 3 groups attached to the carbon-carbon double bond. In order to be cis or trans, you need only 2 substitution groups, 2 groups attached to 2 carbon atoms belonging to the double bond. So in this case, you cannot assign cis or trans. So no cis-trans. There is a different designation that has been applied here, which is called E or Z. In next section, we are going to discuss that.